So now we're gonna see how the methodology of LCA is applied to biofuels. I show you some examples, and even if maybe you have the impression so far that it seems to be so complicated to make an LCA on biofuels, I will show you now it's not so complicated, because if you do it properly, if you're transparent, to take reasonable assumptions, you really can judge and find out what are different environmental effects of biofuels. And as we've learned on the very beginning of this week, again, to remember, when we talk about transportation fuel, you always have to be careful to define and specify the system, especially what is the raw material, what is the conversion, and what are the transportation biofuels you are considering. Secondly, it's very important that you specify the system you're considering very well, and the examples I'm going to show in the following was part of this big project I've shown you already yesterday on the internet with these 30,000 vehicles we have analyzed. And what I'm showing you is the background work we did before we could do it for these 30,000 vehicles. But also in the link from this database, this documentation, you find many of the descriptions that are relevant also for biofuels and to understand the things I'm going to show you today. From my practical experience, from it is with this LCA very important to try also to summarize the key information in a brief way. We have seen that for the biorefinery with the biorefinery fact sheet. We also develop here, we normally do it in most of our LCAs. You always have to make a summary for communication and an executive summary. And again, you see here, this is a fact sheet of biofuels. We will go through that in the coming slides. But the idea is really that on this one pager, you find the key information you need to understand what is the framework condition, what is considered, and what is the result. And what you find here is, on one hand, the process chain you're already familiar with. You also see the main data assumptions in the upper part, so the key data. We need many data, but finally, on the very end of the LCA, you know which are the key data that significantly influence the final result. We discussed yesterday about the driving energy consumption. If you go a hill up and down, or if you're in a flat area, for example, the energy consumption is one of the key data when we talk about transportation systems. So this data must be here, saying I need so many liters per kilometer for the vehicle I have considered. But it's also relevant what is the size of the vehicle, or what is the size of the battery. At least also to identify what are the key and the main influences. And finally, of course, the more you have graphs, yeah, and pictures telling you the results, the easier it is to get a quick overview. So this is at least the summary, and I go it now step by step by going through this fact sheet. I start with the fact sheet on ethanol. We have also seen that picture, starting in nature on the upper part, stopping with a transportation service on the lower part, and in between are the key processes, unit processes you need to convert the raw material to a transportation service. And in purple, you also see some byproduct that might occur and how it is handled. It means an internal combustion engine using ethanol, and the mix means it's a feedstock mix. Because in that case, we analyzed the average European feedstock mix today, in future, and in long-term future. So depending on what is the feedstock for ethanol, of course, also the results are there. And there we have also in future a certain share of lignocellulosic bioethanol included in that mix. And there are scenarios based in the background. We took them from existing scenarios we have in Europe. So in our documentation, we just refer to a scenario saying this scenario says we will have so much lignocellulosic bioethanol. That's why we assume a share of 10% lignocellulosic or even more. Yeah. And then in the upper part, beside the process chain, maybe you can. It's difficult to read the numbers, but it's not so much on digging in the single numbers. It's just to tell you that this is a written explanation about the system. Is this box over there? And in these two tables here, you find the main foreground data. And at least there are maybe 10 or 15 key numbers, yeah, that you have to know to understand the results. And this white table here already is a result table, but I show it to you in the graphs we are producing. So one of these graphs is it's the fact sheet, the lower part for bioethanol results, and in this part here, these are the greenhouse gas emissions. So this is information about the greenhouse gas emission, and this is information about the primary energy demand. So in that project, we have a strong focus on these two, and here you see the greenhouse gas emissions per driven kilometer. Yeah? And this is for today, this is for 2030, and this is for 2050. Yeah, so you see there is a decrease expected also in the energy efficiency in the years to come, in the next 5-20 years, how it might develop. Of course, there are assumptions behind that, but at least we expect a decrease. Additionally, as I mentioned, in some cases, it's really useful to use a range in the results, not to, LCA is an estimation of the impact. So if you end up with a range, with a reasonable range that at least makes sense, but you still see the difference in future is significant. It really goes down significantly. Secondly, you see here in these two graphs, you see this bar is the total value, yeah, which is also appearing here. And the other parts tell you where the emission occur in the process chain. Yeah? And you see this is the cultivation, the transportation, the processing, and the vehicle itself. Yeah? So at least this gives you a more detailed information which of the processes is most relevant. And in the upper part you see that the two big bars are the cultivation of the feedstock. And this yellow part is the N2O emission. So we learned this morning that N2O from agricultural production, and here's much grain and corn involved. You see even more than half of it is N2O emission. Yeah? So and also in the final result, this is the total number. Yeah? You see here finally 15% is from N2O, mainly coming from the cultivation sector. The second biggest one is the processing. Yeah? Most of the current plants, they use natural gas for processing. So the processing is the next big one. And in the processing, you see a negative value for the N2O. Yeah? So the yellow one is a little bit negative. This is due to the fact that in the bioethanol facility, you produce animal feed. And this animal feed substitutes soya feed made, for example, in Southern America. And you get a credit for that because now you make your own animal feed. So in the processing step, that's where we subtract at least the emissions, and in that case, the N2O emissions are bigger from the substituted soy feed compared to the N2O emission in the processing. And at least, so this is really the information where the main emissions occur. So for biofuel, it's always the feedstock procurement or feedstock cultivation, and in most of the times the processing. And then these pie diagrams give you an impression about here you have the impression of it's the same like here, but the blue one tells you this is the cultivation part. I don't see the hood here, so I have to keep staying here. Yeah, it's the blue bar here we have summarized. This is the total fuel supply from cultivation to the filling station. Yeah, and additionally, the red one is the emissions from the vehicle production. Yeah, so we have split it here in the supply of the fuel to the vehicle and the vehicle production, and the green one is the vehicle operation. So you see the vehicle production here roughly has 15 to 20% is really only the vehicle production. And this green part, as the ethanol combustion is so-called CO2 free, so it's counted as zero. But when you burn ethanol in a combustion engine, you still create methane and N2O. Yeah? And this at least contributes still to greenhouse gas emission because they're coming from the stack of the vehicle, and in total they make roughly a 5% is methane and N2O. 20% is the vehicle production, but 80% is the supply of the ethanol to the filling station. The pie next to it gives you the share of the greenhouse gases. The blue one is the CO2, so it's the most dominating one, is really the fossil CO2 from all the different processes in cultivation, in the fertilizer production, in the transportation processes, in the vehicle production. So it's roughly 35% is CO2. A little bit methane is always involved, but a significant share of N2O, which is the yellow part. And this is at least also a minimum that for biofuel systems you always have to consider the CO2, the methane, and the N2O. And you normalize it, CO2 is 1 CO2 equivalent. The N2O we heard this morning is close to 300 per kilogram. So 1 kilogram N2O is 300 kilograms CO2 equivalent. And the methane is in the range of 25 to 30. So 1 kilogram of methane has the same global warming effect in 25 to 30 kilograms of CO2. And finally, you summarize them as a CO2 equivalent. And this gives you at least the information which gases are involved. The list of greenhouse gases is really long, but in these systems, at least these are the key gases. We have analyzed all the other gases. They do less than 1% in the final result. So we skip them normally, yeah, because they are not relevant. The same on the primary energy demand. The first pie is at least telling you where you need most of the energy. Most of the energy in that case is also the supply of the biofuel to the filling station. The production of the vehicle, the red one, is roughly 7%. And for the vehicle itself, for the operation, the light green one is 1%. This means all the maintenance parts are also included, yeah, because a vehicle needs some maintenance, new tires, new engine oil, and so on. And they are also included not only in the primary energy demand, but also in the greenhouse gases. The last one is the most important one because the green and the black tells you that the primary energy, the green one is the renewable energy, and the black part is the fossil energy. And you see there, it's roughly 60% is coming from the feedstock, which is renewable, but still roughly 40% is on fossil based. The red one is normally nuclear, and if you use municipal solid waste also for electricity or heat generation, that's normally counted as others. It's the red one. But very important, here more than half of it is renewable, but still there's a certain share of fossil energy. So at least this is what you find as a result in this analysis. I show you that the same results also for biodiesel. It's the same, more or less a similar process chain, again using a raw material mix. A raw material mix we currently have in Europe and will have in Europe, again seeing the co-products and finally again in the fact sheet of biodiesel, you see the improvement potential of biodiesel in future is maybe not so impressive compared to bioethanol. The main reason is for the bioethanol you can use lignocellulosic bioethanol, straw and wood, which has a much better greenhouse gas balance than conventional bioethanol. But for biodiesel, we don't have such a feedstock. Yeah? So this is still oil and fat based, and improvements there. There are some improvements, but not so much. Impressive to see here that the oil crops, especially rape, they have a high demand on nitrogen fertilization in agriculture. Otherwise, the rape would not grow. So you see here that the N2O, maybe you see here there's the yellow part, the N2O is roughly 1/3 of the final result is coming from the N2O emission. Yeah, so this is really a substantial contribution from the direct N2O on the agricultural field. Yeah, so in that case, because rapeseed is the most dominating feedstock here, but even the soybean or sunflower is still a relatively high share. But you also see that for the bioethanol, for the biodiesel, the share of renewables is nearly three quarters. Yeah, so this is a little bit higher than for the bioethanol because the energy demand of making biodiesel and the electricity demand is much lower compared to bioethanol. Because in bioethanol we need the distillation of the pure alcohol, and that really needs energy to evaporate and get rid of all the water. Again, for the overall picture, the blue one is the fuel supply, the vehicle production, and the vehicle operation. It is very important to know that the diesel vehicles have significant higher N2O emissions at the stack of the vehicle than the gasoline cars. Yeah, so here the green one is a little bit bigger because the N2O emission from driving a diesel car is quite is higher than with a petrol car. So this is very important to really include also the emissions from the stack. And this is just a summarizing of many different biofuels. In the overall project, we have analyzed, I think one is the diesel and one is the, I have to check. No, they are all biofuels, but also biofuel blendings. And the expectation is at least that they all will decrease in future. And the key driver for reduction of greenhouse gas emission is, of course, that the vehicles are expected to further increase the energy efficiency. So if they need less fuel per driven kilometer, this is one of the key driver that really brings it down. And the vehicle we have considered here is an average vehicle, an average sized vehicle. If you take a bigger one or a smaller one, of course, the lines will go up and down. Additionally, as I've mentioned before, I just show you also the table in some more details that finally, when we are going to document our results, we tend really to use ranges. And we have specific methodologies to define some reasonable range to avoid artificial differences between two systems. So if the areas overlap, you see there's no significant difference. But if it's a bigger difference, of course, then it is good. I jump over the e-fuels because I think they are not so relevant in your country in the years to come. If you're interested on that, I can maybe later on, if you have a specific interest how to do it with e-fuel, we can do that. But I keep within the bioethanol. The only thing where bioenergy and e-fuels are somehow connected is only when you take CO2 from a biomass combustion. Yeah, if you take that, then you have a direct link between bioenergy and e-fuel. If you take CO2 from air or for any other source, it's totally independent, the e-fuel. As you're interested in also work on specific processes in making the bioethanol from wood, you know that the process maybe already better than I do. You know that the difficult thing is really to make the sugars from the cellulose. There are many different pretreatment methods and how you do it. And we're demonstrating this technology also in Europe. But so far, we have no commercial breakthrough. Yeah? So there are many enterprises in Europe that trying to develop this process. We have in Denmark a big facility. We have in Germany a big facility. We have in Italy a big facility, but they are all still on the demonstration pilot phase because to really keep that constant production process is still a challenge. Yeah? And really the making the sugars is a big thing. And then normally in the current demonstration plants, they use the lignin to supply the heat and electricity you need for the process. You have seen this picture already in different ways, always telling the same, how to come from wood to bioethanol. As I mentioned before, also the black liquor from pulp and paper production, depending on their specific process. You might have the possibility to also use the sugars from the black liquor, and afterwards you still can use the black liquor for electricity and heat generation. I told about the example we have in Austria. You know the composition of wood and straw. You know how much sugar you can make from different lignocellulosic material, from beech, from hardwood, or from grain straw. And for us, at least in a bigger project, we were thinking about, can we integrate this lignocellulosic bioethanol system in an existing pulp and paper mill? The idea was they have already lots of wood being used for pulp and paper. So for them, it's easier. They know the wood handling. They know where to buy the wood. So for them, they have the perfect infrastructure to also use that. They don't have only access to the resource. They have the existing logistic. They have the infrastructure. And very important, they have the people there that are used to run an industrial facility, because you need people that are trained to run systems like this. And in the pulp and paper industry, you have the engineers that are able to run such a facility. And at least in their overall system, they have quite good opportunities. And this was a project together with the Austrian pulp and paper mill, and we had two case studies analyzed in detail. And this is the biggest pulp mill. This is very close to my hometown. It's only 20 kilometers away, and we used that as a one case study. And this is roughly their energy balance. And the nice thing is also, in the last years, they have much waste heat. In winter in Austria it's cold, and now they build a district heat pipeline with hot water to bring the heat from the pulp and paper mill to the city of Graz, because we have a district heating system. And that is very attractive, because otherwise they had to cool it away and the heat would be lost. But now they have built a pipeline to Graz, a pipeline with hot water in it, not with oil, a pipeline to Graz where we can heat the houses in Graz. So this is a very good way of using all the products. We've learned a refinery, a biorefinery, should make a value of most of their products as far as possible, so they can also have converted the waste heat into heating value, into heat that can be sold on the market. And the sustainability assessment in that specific study was a little bit broader than only focusing on the environmental part. We looked here first on the technology. Yeah. First, you need a technology, good mass and energy balances, and a reasonable system that really seems to be able to work, especially with lignocellulosic biomass. You need to think, do I make a big one or a small one? What are the mass flows? What are the efficiencies? What are the yields? And so on. How much water do I need? And so on. So it always starts with technology first. Next step is to look on the economy. To say, okay, the economy must be really offer a business opportunity. Otherwise, it doesn't help if you have an LCA for a system that is economically or even technically not possible. Then it's lost time and lost money, so to say. So we really started first with the technology, then with the economy, and then with the environment. When we have specified the systems and discussed also with the stakeholders, with the pulp and paper industry. We have 15 pulp mills in Austria, because we have much forests. We also have much pulp and paper mill. So then we made this environmental assessment, and finally also the social aspects, because you also need to involve the public acceptance on one hand, to see how many additional jobs you are creating if you make additional value there, but also in securing the production location. As I've mentioned, the paper demand is going down, so the pulp mill has an interest to have new products, that they can keep their production facilities, that they can keep the jobs there, keep people employed, because industry environment is always changing due to market and different development. So this aspect was very important, to give them an idea what would be a further possibility in future to keep production there, still use the wood, but maybe make less pulp and paper and maybe make more bioethanol. So this was really a key aspect, and we analyzed this also in the social assessment. And based out of that, we created the perspectives for the realization, and also what is still the research demand. Yeah, so what has to be researched, what has to be developed, that this really is going to happen. Um, the final results, I don't show you numbers, I just give you a brief orientation. In total, we have analyzed 12 different concepts of making bioethanol from wood. Yeah? This is not surprising, because in many LCA studies, as you start to compare with something and you want to compare different processes, you soon end up with several systems that somehow seem to be of interest. So at least we have this 12 concept, and we put a value on state of technology, on the economy, and on the environment. And that there are smaller plants and bigger plants. Yeah, so the first ones are really small, because with the black liquor you can only make up to 5,000 tons bioethanol per year, because they have very less sugar in the black liquor. And this is, at least from an economy point of view, a very small facility. And even the lignocellulosic, also Professor Singh mentioned that you need a certain scale, used economy of scale, due to the efficiencies, but also to investment costs, and the investment is high, the capital cost is high, and also the feedstock is high. So these smaller plants, for them it's quite tricky to be that small, and so therefore we added also here additional feedstock here beside the black liquor, also add cornstarch, and for only corn, to also have additional feedstock to see if it then performs better. And you see the state of technology is existing, but the economy has many red signs, so to say. And for the environment, only in few cases, at least, we see there might be a certain gain. Our goal was that the greenhouse gases minimum must be reduced by 35%, and we want to reduce fossil energy by minimum 50%. This was a target we have discussed with the stakeholders, and saying all the system reaching that get a green one, and the others get a red one. If you go to the bigger facilities using black liquor and wood, the size of the plant is increasing. Yeah, so they make up to, in the biggest case, up to 100,000 tons bioethanol per year. This is at least a reasonable size. And here you see the economy looks more attractive, yeah, because it's bigger. But for the technology, we had to make many assumptions, because you cannot yet buy these systems. Yeah? So there is still R&D demand. So the risk of building such a big facility from a technical point of view is really big. So still here is a big demand on state of technology, whereas here for the black liquor, bioethanol production and from corn and sugar, that works. That works, but for wood, in that still has to be developed. But you see the environment is green. So the greenhouse gas reduction of using wood to ethanol is quite well. And also the economy integrated in such a pulp mill at least looks relatively feasible, also from an economic point of view. So the result from this project was that the pulp and paper industry now have a perspective where to go in the next 5 years to come. And they also now are doing much research activities to further develop the technology, that the technology will be ready when they need it. Because they see if pulp and paper is going down, they see there is a need. So they have now created really a strong interest and doing much research on the overall process. I think this research is also focused on the sugar making, because this is a key process, but also then the further processes, and always the question of lignin, what to do with the lignin. To burn it is good for the energy, is good, it's renewable energy, but some guys say lignin should not be burned, because you can also process it to many different products. But anyway. I'm coming now to another activities on the biofuel balance we do so far. This, as I mentioned already several times, this is the Renewable Energy Directive in Europe. And each liter of biofuel in Europe needs an LCA showing that the biofuel has a greenhouse gas reduction minimum today 65%. And the system installed is really from the farmer to the processing until the final consumption. And this is just a directive starting in 2009, where they introduced this LCA thinking, and it's not in the main text. In the annexes, as I already mentioned, is a formula. You don't understand the formula, but it's at least a little bit simplified LCA calculation by looking on the emissions from the cultivation, emissions from transporting and distribution, emissions from processing, emissions from the fuel in use. So at least all the relevant terms for the unit processes are here summarized, and it's a minimum 60%. From this year on, it's 65% that the fossil emission should be reduced by 60%. And this has at least the main simplification in this methodology is, on one hand, they apply only energy allocation. Yeah, so it's only energy allocation, which in most of the cases give you lower greenhouse gas emissions than the substitution approach, but this is for simplification. And secondly, the emissions from the production and end of life phase is not included. Yeah, so at least it's not a real LCA, it's more a well to wheel consideration, because the well to wheel mainly considers the operation phase from agricultural production to the vehicle, but not including the production and the dismantling of the facilities. But as you've seen before, the vehicle production roughly makes 50 to 20% in the overall system. So at least these values are 50 to 20% better, better compared to a total LCA. Yeah? The reason for that is they stop at the biofuel, so their functional unit is grams CO2 equivalent per megajoule fuel. So they stop at least at the fuel, and they say this directive is mainly relevant for all biofuel producers. Yeah? So they cannot change the vehicles, they have no influence on the vehicles, so their business is making biofuel. Therefore, this directive was developed for that. And when they started to develop this methodology, we had very much work, because all the different ethanol producers wanted to know their balance, because they were still discussing about the reduction targets. So we had many bioethanol facilities all over Europe, and we helped them to calculate their initial value. And we did this also for the Austrian bioethanol plant. We have only one. It's close to the river Danube. So here you see the river Danube is running here. And it's a big industrial facility. I think you know how an ethanol facility looks like. They use more than 600,000 tons of maize and wheat mainly. They have also some additional feedstock, but it's mainly maize or corn and wheat. And they roughly make nearly 200,000 tons of bioethanol, and also roughly the same amount, 200,000 tons of animal feed. And really the value from the animal feed from an Austrian perspective is quite good, because we are really avoiding the import of animal feed from abroad. Yeah? So this is really also very strong motivation to not only have the bioethanol, to also have the animal feed. And in fermentation you produce pure CO2. So if you collect that and use it for any purposes, for technical application, but also here for beverages, they also started to collect the CO2. Yeah? And the collection of the CO2 is also part of this formula, because if you this term here, emission saving from carbon capture and replacement. So if you really collect the CO2, you also get a credit in that formula. Yeah? Because on one hand, you need additional energy to collect it and to compress it, but at least you get a credit, because you're really also substituting fossil energy. And we calculated, at least we have only one bioethanol facility, and we calculated the greenhouse gas emissions in grams CO2 per megajoule, and you see the gasoline value is in the range of 90. So the value in the renewable energy is a little bit lower than the real Austrian value, but the green bars with the different feedstocks you see, they have significantly lower greenhouse gas emissions. If you even use this B&C starch slurry coming from a wheat starch biorefinery, this is even having nearly 90% greenhouse gas reduction, because it's a side stream from the wheat processing to different wheat products, and that is also used here. And the current feedstock, as I've mentioned, as it's very close to using corn and wheat, at least that the average value is a 25 gram CO2 per megajoule. And you also see this value is because we use the CO2 from the fermentation and can sell it. So this is also part of this regulation. If we don't do so, the value nearly doubles. Yeah, so collecting the CO2 and using the CO2 is a good thing for greenhouse gases, but it's also a good thing for the economics, because you have an additional product. And if you can make money out of that, that is the concept of biorefinery, to really use all the products you're creating to also make additional economic value. We did the same analysis also for the biodiesel producers in Austria. And biodiesel, you always have to compare to fossil diesel. The fossil diesel has a little bit lower greenhouse gas emission than the gasoline, a few grams less. This is due to the process in the oil refinery. And here again, you see these 6 or 7 different feedstocks we use in Austria to make biodiesel. We have at least very much waste cooking oil in the overall mix. But we also use very much rapeseed oil, sunflower oil, soy oil based in Europe. We also use animal fat, yeah, from slaughterhouses is used a little bit. So they have a good balance, because they are residues. So they have a low emission, because you don't have to cultivate them. And at least in the overall reduction, the biodiesel is higher than the bioethanol. It's in the range of 35 grams CO2 equivalent. So it has a reduction at this time of 60%. And we analyzed this upfront before this directive came. So the biodiesel producers could easily agree to a first target of 35%. And they have also seen that they have the opportunity to go up to 80% stepwise in future. So this really increased the acceptance of this regulation, because the producers saw this is a way we can live, and this is a way to go forward. And of course, it really helps to reduce greenhouse gases. And the introduction of biofuels in Austria was the biggest activity in the last 15 years to reduce greenhouse gases. Yeah, so if you see how much the biofuels introduction reduced the total emissions of Austria, that is the biggest measure taken in the last 15 years. Yeah? So this at least was the target also, to reduce greenhouse gases. Here a little bit a detail to highlight again how relevant it is to at least include also the N2O, especially for rapeseed. You see the rapeseed has significantly more N2O than the soy. The fossil diesel nearly has no N2O in the production phase. There's a little bit methane, but most of the fossil diesel is coming from the CO2. But for the biodiesel rape, it is nearly 50-50. And of course, the waste cooking oil also has no N2O, as it is a residue product and not directly affected by the agricultural N2O emission. Yeah, and based on this renewable energy directive, it is mandatory that each country in Europe makes an annual reporting about the biofuel. Yeah, how much biofuel they produce, how much they import and export, what is the feedstock, and at least so every year there's a report coming out from our ministry telling exactly how much biofuels we're going to have. And this picture is a quite quite interesting picture. You see here, he is harvesting some grains, and these are photovoltaic panels in agriculture. So this here's a full agricultural photovoltaic. This is in the years to come now an idea to most efficiently use the ground. And this is just a pilot place in Austria where you really see you can combine different functionalities on the field. And this is also when you're calculating the area demand of biofuels. If you have also photovoltaic here, you need less land for cultivation. Even if you do a photovoltaics like this, they have animals running around, the chickens and the goats. Yeah, they are used to have the grassland below. So it's also a double function of the same area. You make electricity on the panel as a roof, and below you have the chickens or the goats. So this is also something coming, because the more efficient you are able to use the land, of course, the better it is. And then we have really established a system to prove the sustainability. Yeah? So there's really a system in place that starting with the farmer. So the farmer has to report certain data, mainly on yields and fertilizer use. He has to report in an electronic system. Yeah? And so each ton of rapeseed or grain he's selling to a biofuel producer, he has to report some key data. So it's not hundreds of data, it's maybe 20 or so. I don't know the details, but that's all going in a system. And then the one who is transporting from the farmer to the bioethanol facility, he has also to report how many kilometers he did take, how much load he transported, yeah, because all this data is relevant. And then the biofuel producer also has to report, currently on a monthly basis, to report how much energy they needed, how much bioethanol they produced. And at least this is all done electronically. So finally, you know, for each liter of bioethanol, you know exactly which feedstock has been used. And even if that sounds maybe like much work, finally, the main idea is really to make sure that all the biofuels used in Austria or in Europe really fulfill all sustainability criteria. Yeah? Because sustainability is the key priority, and only using biomass is not a guarantee that it's sustainable. Yeah? You really need to fulfill certain criteria, and this is at least a good system being established already since nearly 15 years so far. And I personally would like to have such a system for all products. I told you about the automotive industry. They also are going more and more in that, because they also have to report quite soon about the carbon footprint of making their vehicles. Yeah, but you can also do it for each product coming from agriculture, but also for each laptop and each mobile phone. And so in my thinking, of course, I'm quite sure it will come. The question is when it will come, but I'm quite sure this system will come. And there are also limits will be set. If you are above a certain amount of greenhouse gases for a laptop, for example, maybe you're not allowed to sell it on the market because, and you also have to say it must decrease, and you have to prove that you decrease it. Maybe you have also seen, I've shown you the liter of milk where you find that. I bought a sport shoe recently, and also in the sport shoe they told me it's a 10 kilogram CO2 by making this sport shoe. So more and more companies also reporting currently voluntarily about their greenhouse gas emissions. So LCA is really a part of our daily life, and it will even become a more relevant part. So we need many LCA experts, yeah, to do all this work recently on a good way. And so at least this is the proof of sustainability. Yeah. And here's just some key facts if you're interested that how much Austria is using on biofuels. I don't want to go through the details numbers, but it's at least biodiesel and bioethanol being used as a blending. Yeah, so we have the B7 as diesel and the E10 for gasoline, where we can use use it. We have only ETBE is a very, very small fraction. Also the HVO is very less, and the biomethane is nearly invisible. But anyway, it's the right way. The interesting thing is if you look on this reporting of Austria, in Austria we use very much waste cooking oil for making the biodiesel, and this has a very good greenhouse gas balance, as we've seen. Yeah, and you get a better price if you have lower greenhouse gas emissions. Yeah, and so most of the biodiesel produced in Austria from waste cooking oil is exported mainly to Germany, because in Germany the price level in general is higher, and they pay more for a biodiesel with low greenhouse gases. So the curious thing is, on one hand, Austria is exporting biodiesel, but as we need biodiesel also in our country to fulfill the requirement, we're importing biodiesel, yeah, with a lower greenhouse gas saving, I assume also a lower price. Yeah, so this is also part of the economics. Yeah, that you produce it and you export it, and the same product you're importing for any reason. And this is really happening in Austria, because Austria was a front runner in collecting waste cooking oil. And I think this is a really good way to start with biodiesel, to collect at least the waste cooking oil. So at least you see here, roughly you can say, if I'm substituting 1% gasoline or diesel, you reduce the greenhouse gas emission by 60% in average. So it's not 100% climate neutral, but it's at least on the right track. Okay. The take-home message here is, what do you need? You need a clear description of the biofuel production is necessary. You need an energy and mass balance. Consider the co-products is essential. The main focus is always on greenhouse gases and primary energy, as we can judge them in LCA quite well. Yeah, this is important. Biofuels have lower greenhouse gases, but still further reduction is necessary, because the things are going on. NTO is always visible in these agricultural-based biofuels, because the NTO is so relevant. So at least advanced biofuels made from lignocellulosic become more and more technically and economically feasible. They promise to have a reasonable greenhouse gas balance. Austria is having roughly 10% renewable energy in the transportation sector, but you also count for the electricity used for trams and trains and so on. That's also in that package. So roughly 7% of them are biofuels. So the biggest share of renewable energy in Austria is in the transportation sector is biofuel. And last but very important is really to guarantee the sustainability, to really show that the systems are sustainable from the very beginning. Clear targets are set, a clear system, clear electronic way to guarantee this overall certification project, to make sure that each liter of biofuel really has a significant greenhouse gas reduction. Yeah, that was it so far from my side. Do you have any questions?
Hello. I just wanted to clarify something in one of your slides regarding 12 concepts of sustainability. There, plus minus, and in brackets you are keeping minus minus plus minus. It was not clear to me actually. What do you mean by that?
I show it
Yeah,
to you.
please.
Yeah.
Yeah,
The scale here is relatively simple. A green plus means the technology is existing and state of the art. Yeah. And the red means it's not good, and the brackets was based on the sensitivity analysis. Yeah. We change the parameters and see if in a changed technical setup, maybe this system becomes economically feasible. And here, for example, you see under specific conditions on the green side. So this is the bracket is a part of the sensitivity analysis, which is very relevant. And you see, you can do it economically, environmentally friendly under certain conditions, but you see it's very hard because you have two red ones.
Okay.
This is just to get a feeling. You have the average is plus, but if you're not careful, you end up with a minus.
Okay.
So it's really for high aggregated assessment, but
Okay.
it was easy to communicate that to the stakeholders.
Okay. So another thing is you also mentioned the biofuel production from lignocellulose is currently mostly from paper and pulp industry, right?
Yeah, this is state of the art. Yeah.
Okay.
So not all pulp mills have sugar in their pulp,
Okay.
but this is state of the art, and in Europe, I would say that only a few plants doing so. But the total amount is very less sugar in it, so the total amount of ethanol is quite limited. This is state of the art, but all the other from straw and wood. Main focus is, at least in Europe, on straw more than on wood, I would say. Only the northern countries, Norway, Sweden, Finland, they have much wood. But generally, the big countries, Spain, France, Germany, Poland, they have much straw. So a bigger focus is on straw.
Okay. Okay. Thank you.
You're welcome. So the rest was clear. Very good. Do you have any questions on your homework? Or was it clear? Okay. So we make a brief break and then continue. I don't know what's the schedule, but a 10 minutes break or so, and then we continue with the last.